Guys, you know. And one thing I'm definitely not going to do is the whole woe is me thing, because I know that there have been plenty of people who have been in this situation already, and so it's an old hat, unfortunately. Normal probability distributions. So we talked about normal distributions, and we've talked about probability. So it kind of makes sense that at some point we would put it all together and talk about the two ideas as one, normal probability distributions. The normal distribution, as you might remember, is the bell-shaped curve. We have those rules, the 68, 99, 95, 99.7% rule, the empirical rule. We did some work with that back in the first unit, which might seem like a lifetime ago now. But you probably didn't see this definition, or at least I didn't really talk about it. A continuous random variable whose distribution when graphed is bell-shaped. First time I read that definition to my first stat class, they're like, the only thing that I understood out of that was bell-shaped. I'm like, fair enough, fair enough. A continuous random variable. All right, random variable, right? So a variable that represents outcomes determined by chance. All right, so you're talking about rolling a die. Your random variable would be the outcome when you roll the die. You know, the numbers 1, 2, 3, 4, 5, or 6. Right? But what does it mean to be continuous? Right? So I'm going to bring it in on that. Continuous values that are determined by a measuring device. All right. In the past, I would go with the definition as values that are determined by measurement, and that only confused people. So by some sort of measuring device. So when you're measuring the length of something, the weight of something, the time that something takes to happen, you know, you're using a device, you're using a ruler, you're using a scale, you're using a timepiece. You know, those devices allow for what we call continuous data, right? Because if I were talking about discrete data, I would be talking about like something that I could just determine its value just by counting. You know, there are 14 students in my class. You know, there are 10 light bulbs, you know, in my house, you know, and like my spare light bulb, in the box of spare light bulbs, you know, that kind of thing. You're just counting things up. There are 3 starships, I think. No, I got 4 starships and a star base, you know, but that kind of thing. You know, you're just counting them up. But if I say that I want to know the temperature can be represented in decimal form. You're not gonna look at temperature. Now you can look outside and say, well, the sun's shining. I don't see any precipitation. I don't see any frost on the windows of my car. I don't see anything like that. So it's probably pretty warm. Right? The birds are chirping, so I'm using other senses. Okay, so feels like 70 degrees. You know, you can kind of make an educated guess, but you're not going to point at the temperature and be like, all right, it's 70 degrees. That's not how it works. Right? What we're going to do here is learn how we can determine probabilities for continuous random variables. All right. So when I say, for example, that what is the probability that the length of time it takes a person on average to complete a race. I want to know the probability that they're going to do it in less than 8 minutes. You know, maybe that race is 1 mile long. You know, probability that, you know, if I really think they're pretty serious runners, less than 6 minutes, less than 5 minutes, you know, and so on. Right. So it's specifically related to units of time. Right. And then what we're going to do is we're going to take that and use it to project out to entire populations. and see if we can draw conclusions about a population as a whole. All right. So the first thing that we want to do is get a look at this graph here. Look at that baby. If you remember college algebra or pre-calc or any class like that, you probably remember creating graphs, but I would imagine you don't remember creating a graph quite like this. Right? Fortunately, we have Desmos, which does that kind of thing for us. Now, it's really kind of entirely up to you whether or not you want to do what I'm about to do, but it's another thing like what I did in the last unit where I created the Desmos and then I shared it with you. I'm going to do the same thing, right? And I'll also show you some shortcuts that you can use, right? But I did want to show you how we can construct this so that we could use a Desmos calculator to compute probabilities for us, right? So y equals fraction. You have an e, exponential e, approximately 2.718. Yeah, but anyway, it's oh, you know what? It's a legacy typo. This is supposed to be times 2 pi. I fixed it in every other class except for this one. So anyway, raised to the, I'm going to write it as negative 0.5 times another fraction, x minus mu. Now, getting a mu on Desmos is kind of a pain, unless you have an add-on. I mean, you could try to type in mu, but it's kind of, like I said, it's kind of a pain. So what I do is I just use a capital M. That's not a capital. And then a capital O, or whatever symbol you want. But I like the O because that looks close enough to a sigma that it kind of works. You can copy and paste Greek letters, and what I'll do when I send the real one out to you, when I send the real version of this script out to you, I'll send it with the mu's and the sigmas in there. But I just wanted to give you a little bit of a sense. Right, so capital O square root of 2 pi. And then it asks you to add a slider because this is a function of y dependent on x. Everything else would be considered a constant, and that constant can be changed to whatever you want it to be. So I'm going to hit all, and you can see I got a little hump there, a little hump in the graph. All right. So this is essentially what the normal distribution graph looks like. Just making sure I typed in everything right. All right, now if I slide this slider along, you can see it impacts the graph. All right, same idea with the.
How do you type the square root symbol in Desmos for the bottom part with 2 pi?
Good question. There's right next to the pi. There's a little square root symbol right there.
Oh, yeah, I'm not on. All right, I'm on desktop, so I might not have mobile. I can figure it out. It's no worries.
Okay. If you need a square root, you can raise it to the 1/2 power, and that'll do the same thing.
Oh, perfect. Thank you.
No problem. So, yeah, I mean, we got the sliders here. We can manipulate the mean and the standard deviation. For a standard normal curve, we started off at 0, and we have a standard deviation equal to 1. But like I said, we can let it be anything. You know, we can just slide it on down the line, and we have a nice looking normal curve. Now, if you want, you can manipulate it so that you can bring it in a little bit more. That's entirely up to you. You know. You hit that little monkey wrench there. Since we typically only go negative roughly 3 to 3, I can do that. And then for my y's, I can make it, and I really don't need anything less than 0. So I can just make that 0 and then make this, you know, something small like 0.5. And then when I do that, you see I have much more normally distribution-y looking graph, right? And so that's where this graph comes from, right? Just that relationship. Now, I always say this is kind of an old joke. It's not really a joke. I don't know how else to describe it, but it's kind of like an old thing that I like to say, is that I'm smart enough to understand these concepts, but I'm also smart enough to understand that I don't know that I would have come up with these concepts on my own. You know, there's some heavy duty stuff here that whoever created this, like somebody created this formula for a normal distribution, that person is like beyond intelligent, because I always consider the fact that I'm using graphing technology to help me understand something that somebody else created before graphing technology existed. And it's like, whoa, how did they even come up with that? And it's fascinating, but it's also humbling. You know, so total area under the curve is equal to 1. That's old news. Every point has a height greater than or equal to 0. And the reason why we can say that is because of the concept of an asymptote. If you remember that from really any math class that involved graphing, an asymptote is a line that a curve approaches. And if, depending on the nature of things, if this curve could go on forever, we don't assume that it can. But if it could ever actually get out to infinity, that's when it would come in contact with this horizontal line. All right, so let me just expand this. So eventually they'd merge, but only if it could get out to infinity. So practically speaking, it's never going to get there, right? Because we can't get out to infinity. So how could we assume that the curve would really be doing what we're going to say it's going to do out at infinity if we can't witness it, right? But we can say that the heights on the curve would be greater than 0. We're just going on faith and saying that it could be equal to 0. Right? The standard normal curve is centered around 0 with a standard deviation of 1. And those horizontal axis measures are in terms of z-score. So we're going back to the concept of the z-score. Right? The empirical rule, about 68% of the data lies within 1 standard deviation of the mean, about 95% within 2 standard deviations, about 99.7 within 3 standard deviations of the mean. Right? Here's a nice little typo for somebody. Assume that the mean is 0 and a standard deviation of 1. Find the probability of each using, well, the graphing calculator is fine, but I would want to say the Desmos calculator. And so this function is going to be different. Right, and I'll talk to you about what it'll look like for real on this display. Right, so there is a tool built in to the Desmos calculator that evaluates probabilities in the standard normal curve for us, which is great news. It's like ideal. And it goes back to what we were talking about before, like way before, is that technology, it lines up with statistics beautifully to the point where if you're not using technology, then you're not really doing yourself any favors in terms of your understanding, right? But before we get to the calculator, let's talk about what this would look like in terms of just a quick sketch, right? So the standard normal curve is centered around 0 and measured in terms of single z-scores. So 1, 2, 3. I could also go left, -1, -2, -3. Be a little proactive here. Gonna have to do it anyway, so why not, right? So between 0 and 1.5. So here's where roughly 1.5 would be, only roughly because I can't draw. And here's where 0 would be. What I'm looking for is the area between these two locations. All right. So we know the total area under the curve is equal to 1. So that means, assuming it's symmetrical, which it is, that means that 0.5 would be the area on either side. So I'm expecting a value that's going to be a little bit, maybe a lot less than 0.5, but it's definitely going to be less than 0.5. So I'm looking for the probability that z is between 0 and 1.5. So the big question would be, how can I do this on the calculator? Now, I can tell you that there is a technique involving integral calculus that'll do it for you. It's not pretty, but it is related to this function. And so I don't know how many people have experience with any kind of calculus, but I like to show this technique just because I figure there's always somebody who's interested, right? So if you have any experience with calculus, then what I'm about to show you is related to that. If you don't, then just ignore everything I'm saying, at least for the next couple of minutes, right? So what you'd be looking at is the area under the curve. And so if you wanted to, so this is again, this is a calculus explanation. So we would be looking for the area under this curve. So let me just grab this real quick. So we would be integrating this over the interval of a to b with respect to x. All right. And again, if you don't have any experience with calculus, it doesn't make any sense, doesn't have to. Right? Maybe if you ever take a calculus class, it will make sense. All right. So what I would do is I would use in Desmos, I would use my integral function. So it's under miscellaneous. You have this integration rule here that you can make go from a to b. But I would have to put all this information in. And so I'd look at it and say, well, I don't want to retype all that. So what I do is I tap on this bad boy here, duplicate this, and modify this one here, popping in that integration, going from a to b, and pop in a dx. And again, we need sliders, always need sliders. All right. And so this is reliant on whatever we have for mu and sigma and a and b. All right. So in this case, I'm just going to snag this real quick. We're going from 0 to 1.5. All right, so my a value would be 0. And my b value would be 1.5. And so we get, as a result, because this integral is your area, so about 0.433. Now, if I'm a student that doesn't have any experience with calculus, I'd be thinking, wait, so does that mean that I am now going to fail the course because I don't understand this crazy calculus stuff you're talking about? No. What it means is that you're just going to be waiting patiently another 20 seconds for me to show you that Desmos has this function built in already. and it's not anywhere near as complicated as this. But I like to show this little approach here for my calculus people who have a little bit of background and want to see that connection, right? Because whenever you talk about, again, if you have any experience with calculus, you can't hear the term area under a curve and not think integral. Right?
Professor Khan?
Yeah.
I'm very mad at you right now.
Why?
Because I'm not happy with my grade. I had to say something. I'm
No,
so
I appreciate
sorry.
it.
Huh?
I appreciate it. You understand that you're saying it to the entire world, though, when I post this all up on YouTube, right?
Oh my God, I'm kidding. I'm just kidding. I just wanted to hear what you have to say. I'm sorry.
Yeah, no problem.
Sorry. I'm just kidding. Bye.
Yeah.
Carry on. I'm sorry.
Just as a general rule of thumb, folks, make sure I'm not recording if you want to talk about it. Personal. Anyway, so we got 0.433. That's the area under the curve. So we're good there. Now what we want to do is learn the Desmos way of doing it, the built-in function, because it's going to be a whole lot easier, I promise. All right. So what I'm going to do is I'm going to, well, I'll save it. I'm kind of a hoarder when it comes to my Desmos work. So I'm going to save that. Calculus, normal curve. And if anybody wants that, I'll make it available by request. I'm not going to put it into Blackboard because I don't want people to look at it and think, wait, I need to use this, you know, because they forget the context and so on. And I don't want to frighten anybody. So go to function. Under distribution, you see that there's an option for a normal distribution. So function, distribution, select normal dist. All right. Now it defaults to the mean and standard deviation of 0 and 1. All right. So I like to type it in anyway, though. So normal distribution 0 and 1 gives us the same picture. All right. I rescaled it to make it look nicer, and I'll do that again. We did -3 to 3 and 0 to 0.5. So same graph. Now, when I tap on find cumulative probability, it gives me an opportunity to plug in a minimum and a maximum value. All right. So based on the problem that you're working with, the minimum corresponds to the lowest value related to the shaded area, and the maximum, same deal, except the highest value. So what I would do is I would just type in here 0 and 1.5. And you see that not only does it spit out the answer, this one is a little better than the one that I did with the calculus. It even gives you the shading. And that's really all there is to it. So when, I mean, look at all that calculus that we avoided just by knowing how to use the Desmos calculator a little bit. Now, there is a little nifty shortcut if you like, and it's up to you, especially if you're following along on this and you want to make your own. I've been encouraging that over the course of the semester. What you can do is you can make this A for the low bound and B for the upper bound, and create sliders so that I can just slide back and forth here to different A and B values and not have to worry about typing in every single time. And so now I could use this for multiple situations if I want to. Right? It defaults from -10 to 10, but that's usually enough. And so what I can do now is if I need something like 1.28, you see here it's only going to nearest 10th. So a little nifty trick. If you tap on one of the bounds, let me show that again. So you see that -10 and the +10 right under the A? If I tap on one of those, and I could even just tap on the A if I want, I could change my step. All right. If you change your step to go by hundredths or thousandths, then it'll give you a more accurate way of moving your slider. So what I typically do is I go to the nearest hundredth, and I do that for both of them. So I change my step to be 0.01. So it goes, assuming I did it right. Jeez. That should have worked. Let me try this. Well, that's infuriating. Okay, well, worst case scenario, just type it in. But for some reason, I don't know why that didn't work. It almost always does. For some reason today, it just doesn't want to work. So you type in the 0 here and the 1.5 here. But the step, by making this 0.01, would allow it to go the nearest hundredth. And for, like I said, for whatever reason, it's just not working in this case. When I send you the official one, I'll post it on Blackboard. It'll work because I know the one that I created already does work. I just don't know why it's being difficult right now. Must have done an update or something. Either that or I'm misremembering. I don't know. It's possible. But anyway, either way, you manipulate the A and B values here rather than doing it in your normal distribution so that you don't have to mess around with the min and max in there. Either way, you get 0.433. Right. So then you look at something like this, which is saying the probability that Z is greater than -3. So when I look at this, I would be saying that my low value here, the min, is -3. The high value would be like infinity. So it's telling me to get everything to the right of -3. So that should amount to damn near 1. Right? So I'll go to -3 on this one. And then I'll slide my slider all the way to the right for the 10, for the infinity. And you could see, like as I manipulate my slider for these high values for B, you see that after a while it stops changing the decimal under cumulative probability. So once you get to a large enough value, and that's the beauty of the slider, I don't have to test multiple values. Once I get to a large enough number, you see it locks on to an actual probability. That's how you know that you've arrived at the correct probability. 10 is usually enough because there's an infinitesimal change in corresponding values, but sometimes you don't want to take the chance. So if you're unwilling to take the chance, then make this 100 and see that there's no difference in the probability value. And so it rounds to approximately 0.999. I don't know, for this kind of question, it sort of feels like that's what I would have guessed. You know, if I gave you that shading and I said, well, what's the probability? You know, I would be thinking, well, it's probably not 1 because, you know, to have everything accounted for, probably not. I feel like it's probably like 99.999%, you know, something like that, you know, so it's got to be in that neighborhood. But yeah, if you're not sure, then you just try it with the Desmos calculator and you go from there. Right, to the left of 1.28, just ballparking it. So that's the probability that Z is less than 1.28. So I would slide, and again, I'm just going to go back to the default settings here. I'm going to make this -10 to 10. So my high value is 1.28. So it's only going in nearest tenth. So I'll just type it in. And on the low end, the A value, I want that to be something really small. All right, so something close, that would be an approximation of negative infinity. But again, you see, as I slide this slider, there's really not much change, especially, you know, even for like -3, -4, you could see the first three or four values aren't changing. It's everything after that that's fluctuating until even those don't change anymore. All right, once it locks in 2046 at the end, then that's really it. And so we know our probability is about 0.899. Well, actually 0.8997, if we're going through significant, that would be 0.900. Or you could just write 0.9. Right. So then I'll look at number 5 here because it's right there. It's within view, and it's almost identical. And actually, I can tell you, in terms of the work and your expectations, it's actually identical.
Professor?
Yeah.
For the I see on the slider there you have like A set at -10. Can you explain, like, because on the paper it only goes to like -3. That's just confusing me a little. Like, can you explain that?
Oh, because the actual graph goes to negative infinity. So
Okay.
we want to go as low as we can based on the sliders that we have available. So
Okay.
you can go -10 based on that slider, or you could even make it go further. Go as far as you want.
Oh, okay. So it doesn't really matter what the minimum is.
Right, as long as it's you know, since we're trying to get values that are less than 1.28, we want to be as close to infinity as we can get without losing any accuracy.
Okay. Thank you.
So for this one, it says Z is at most 1.28, which is a less than or equal to. I can tell you that less than or equal to versus less than, sorry, there was schmutz on my screen. They have no difference in terms of how they're computed, right? Because the actual line at 1.28 has no width, right? So it doesn't contain any area. And so 1.28 versus less than or equal to 1.28 versus less than 1.28 amounts to the same thing. So then along those same lines, we have to the right of 1 or at least 1. All right. So to the right of 1 is going to be the probability that Z is greater than 1. Versus at least 1 follows the same idea. Except the only thing that's changing, that little symbol, greater than or equal. But the answers are going to be identical. Right? So when it comes to our sliders here, the A value is going to be 1. That's our low number. All right. Where does the shading start? That's your minimum. Where does the shading end? That's your maximum. But again, I mean, unless you want to put in infinity, which you could do, you usually just put in some acceptably large number, and 10 is a typically good number, right? Because you can see here, hopefully, that we're looking at 0.158655. I make it a little bit less, 158,655. And make it a little bit less, 158,655. It doesn't really, like, even 5 is still good. You know, it's when you get to 10, that's when it locks on to the true probability. All right, so we're looking at 0.159 approximately. I got a little extra squiggle there. All right, so it ends up amounting to the same thing. And I get that extra stuff here. All right. So that's the concept of just the standard normal curve. And, you know, while we're here, we might as well talk about the one case that we worked with, or one of the cases that we worked with back in the first unit, and that involved the empirical rule. And you can see here that if I make it go from -1 to 1, just kind of looking back up here, I get I get 0.68, approximately 0.683, but still 0.68. You know, if I go from -2 to 2, I can get it to lock on. Come on, you. -2 to 2 is about 0.95. And -3 to 3. About 0.997. Right, so this is actually verifying the empirical rule. It's not that this came from the empirical rule, this normal distribution stuff. It's the other way around. The empirical rule is really just 3 special cases of what we were just talking about here. All right. So then we get to a point where we want to start kind of applying this, and there's a couple of ways to handle it. You know, so when we're talking about, oh, and here's another kind of typo. This is for the TI calculator, which is not applicable here. So we're looking at trying to go the other way and use this to determine percentiles. We talked about percentiles in the first unit. And so if I wanted to know a particular value that separates the top 10% of the class from everybody else, then I would want to know the 90th percentile. Now, the thing is, I don't know where that would fall necessarily on this graph, so I have to estimate. So what I would do is I just kind of ballpark it. I know 50% of the data is going to be at the halfway point, which is by definition. I'm going to shade most of the graph to get me to about 90%. This is 0.9. The thing is, I don't know the z-score. So there's 2 ways to do it. One way is a little easier than the other, but that way requires you to know another function in Desmos. And again, I'm going to send you all these functions. I'm going to jazz it up a little bit with some notes, you know, like this is for this case, this is for that case, and so on. But for the most part, it's just going to be what you see here. All right. So one way you can handle this would be to say that I have z, the probability at z is less than some number, right? So we don't know what that number is. So I could say question mark. I could put a variable in there if I want. Z is less than, you know, p for probability, a for area if you want, is equal to 0.9. So I know that this is going to have to go to -infinity. And we said previously that that's basically saying just go to -10 and you're good. So what I would do is I would slide this slider until I got as close to 0.9 as I could get. But even there, you see that there's some issues, right? Because I can get pretty close, like 1.4 got me a little bit over. 1.3 is a little bit closer to being right. 1.2 puts me under. So this basically boils down to a little bit of trial and error. So I know I'm in the neighborhood of 1.3. So then it's like, all right, well, 1.29. That's why I'm really kind of bummed that this step part of it isn't working, because that makes this whole thing actually a little bit more palatable. Maybe it's really just needing me to, no, I don't know why. I don't get it. Because I know if I put in a 1 there, it goes by ones. If I put in a 0.1, it goes by 0.1. If I put in a 0.01, yeah, I got nothing here. I have no idea why it's not working. Well, anyway, we have an idea. It's like in the 1.2, 1.3 interval. All right, so somewhere between 1.2, 1.3, what I could do is I can make it like 1.29. Ooh, so close, 1.28. Oh, maybe 1.281. Oh, not bad. That would round to it, but maybe something is exactly it. Oh, that's as close as we're going to get, I think. So about 1.282. And so it's like, hey, if you're happy with the guess and check approach and you get something that's close enough that we could say that it's reasonably accurate, then you could go with that. But, you know, there is the idea that there's got to be a better way, right? So that's part of it. So by guess and check, Z would be equal to 1.282. Right? Obviously, it would be equal to something a little bit more precise because I didn't hit directly on 0.9, but I got pretty close. So maybe it's like 1.2817 or something like that. But like I said, there's got to be a better way. So here's the better way. So you go into functions, right? You have this inverse CDF. Oh, sorry, we don't do that yet. You got to tell it what kind of function, normal distribution, and then inverse CDF. Right in front of me. Oh, did I actually? I might have gotten it backwards. It's just weird because it has built-in stuff that you have to take out in order to make it work. Oh, could it actually be? Maybe I'm thinking of the wrong thing. Hold on. No. I might be misremembering something here because and now I'm wondering if I'm misremembering more. Oh, it's a PDF. Oh, okay. Nah, I'm misremembering something. I don't know what happened here, and I don't want to waste everybody's time. Just gonna try one more thing. Nah, I'm not remembering it for some reason. I don't know, but I'll figure it out later. Anyway, we could at least work with this technique. So how does that translate to something like Q3? Not very differently. Q3 is the third quartile. Which is the same as the 75th percentile. So basically, we're doing the same thing, except we're looking for 0.75. Right, so that part should be reasonably understandable. All right, so on the low end, you know, -10 is fine. But then on the high end, we want to scroll around until we get close to 0.75. And then we start dialing it back. So we try like 0.65 maybe. Take a look. Ah, it's just a smidge too low. 6. Ooh, almost. It would round. it would round and be close enough, 0.67. Even better, 0.68. Too much, so maybe like 0.675. So then pull it back to 674. And then maybe like throw a 1 on at the end. It's pretty close, but it's pretty safe that, you know, if I do 6745, that we're somewhere in that neighborhood. So we could say approximately 0.674675. Right. So there's that part of it. But yeah, I'll work on what the other thing, and maybe I'm just thinking of a different calculator. I don't know what the hell is going on sometimes. So the last thing we're going to talk about is how we could do this with like real data. Now this is kind of a stretch to call this real data, and it's also kind of like I got this problem from a textbook like 20 years ago. And the more I look at it, the more I realize it's like borderline offensive. Like, why are we talking about the weights of women? You know, it's like, it's just like the one thing, you know, like you ask a woman what they want to talk about, they're probably not going to talk about weight, and they're not going to talk about their age. And I think that's probably the same for men too, you know, and everyone else. So I'll take it as a typo that this problem should probably be updated to kind of like be a little bit more consistent with, you know, just being respectful of everyone. So so yeah, I'll take, and actually, you know, I'll even jazz this this bonus opportunity up. Instead of just sending the typo saying, here is you know, like, this is the problem, fix it. What you could do is, for 2 bonus points, send me a new scenario. You know, like something a little bit more interesting. Not weights of women. Let's talk about like you know, like whatever you can think of. Just something clean. You know, just something a little bit more interesting.
Oh, so what I'm understanding, in addition to that 3, that's 2 points, so that's 5 points total we get for extra credit.
In addition, so it would be 1 point for pointing out the typo, if anybody just wanted to point out the typo.
Okay.
And then 2 points for sending a revised problem. So total of 3.
Okay. Awesome. Thank you.
No problem. So what we could do for this question here, I mean, the numbers are fine, so we'll work with that. We have a mean of 143 and a standard deviation of 29, right? So what we kind of have is a little bit of an issue in that what we were working on with the previous page was talking specifically about the mean and standard deviation of being 0 and 1 respectively, right? So there's 2 ways to handle this, but one way allows you to work with the same calculator repeatedly and not having to make any kind of meaningful adjustments. So what we can do is find the z-score for 150 and the z-score for 180. So we're reframing the problem. All right. The thing you have to remind yourself is that z is equal to x. Well, in the past, it was x minus x bar over s. Now it's x minus mu over sigma. All right. Conceptually, no different from the mean and standard deviation, or you know, how it was making up the z-score formula before, but now it's in the context of population rather than samples, right? So we would crunch out 150 minus 143 over 29, and then 180 minus 143 over 29. And you could even do that in the same calculator. It's not a big deal. You know, division tool, I like to pop in the division first so I don't have to worry about parentheses. So 150 minus 143 over 29. So 0.241. 3 significant digits so we don't lose any accuracy. And then just change that 150 to a 180 and we get 1.276. All right. So that allows us, I wonder, that would have been nice. I'm just going to steal my scales here. Thought maybe I still had them in the old clipboard there. It allows us to use the graph without having to rescale it to something other than 0, 1, 2, and 3 and the negative counterparts. So 0.241, just eyeballing that. And then 1.276, again, quick eyeball. And so what we're looking for is the probability that Z is going to be between 0.241 and 1.276. So we just slide our sliders or type it in because these are three digits, 3 significant digits. So 0.241. And then on the high side, 1.276. And you can see the equivalent part of the graph is shaded from what we did on paper. So that's pretty good. Now let's see what that gave us in terms of a probability, about 0.304. All right. So, you know, in this case, again, we're talking about a dated concept here, but population of weights of women. With that information, this is telling us that the probability is about 0.304. A person would fall in that interval. All right. So, you know, we can get some valuable information depending on what your topic of interest is. You know, so if you have, you know, just I know there's a lot of runners out there. You know, you have some information about your own running times over a lengthy period of time, and you want to know, you know, like on any given day, what's your chances of, you know, achieving a particular goal? Like let's say you do want to do a mile in less than 7 or 8 minutes or whatever. You know, you collect data over a period of time. And maybe you're kind of hovering at the 10-minute mark. And you're like, well, what are my chances of actually getting to my goal of doing it under 8 minutes? Well, if you know that your mean and standard deviation are, and you would do this by data collection, I mean, we cover that in the first unit, you take all your times, whatever it is that you collect over a period of time, find the mean and standard deviation, create a z-score for the goal time. Like you want to do it in 8 minutes, create a z-score for that, and then run it through the calculator here, and it'll give you a sense of your chances. Right now, is it going to be like ironclad? No, because you're not working with a population necessarily. You're working with maybe a large sample, but the idea is that eventually, if the sample is large enough, we can use it to replace a population. Right. So that's where we're going to leave it for tonight, because number 2 is kind of reliant on that function in the calculator that I completely forgot how to do. So we'll come back to that on Monday. But yeah, like I said, I was going to cut it a little short tonight. So that's where we're at. So let me stop the recording, and I'm going to